So I'm getting a similar phenomenon to the previous video. When the points that I compute now are circumcenters. Let me explain to you what I'm doing here. So let me pick a better triangle. For example, this one. Okay, and I'm going to start from a blue regular n-gon, in this case n equals 5, and a point P somewhere. And for every side of this n-gon, in this case I'm using the side here on the left hand side, okay, I'm going to compute, in this case, the circumcenter of that subtriangle. Okay, and I have a whole fan of triangles, so I can get 5 circumcenters. Let's go to the next triangle. This is the next side of my polygon. Here's a circumcenter of this brown triangle. So if I go to the next one, I get that. Then if I go back, I have some obtuse subtriangles here. Therefore, their circumcenter falls slightly outside of the triangle. Let's go back to this one. This one is quite obtuse. So there it is. Now what you notice, and here n equals 5, obviously I can always draw a conic about these 5, right? I've noticed that, and perhaps I've already said this in a previous video, that this conic, this 5-point conic in the pentagon will always have one of its foci. And P is going to lie, let me get rid of this construction triangle here, on the major axis of this conic in such a way that if I rotate P about a circle centered on O, I'm just rigidly rotating this 5-point conic. Its eccentricity is preserved, and its eccentricity only depends on this distance between P and O. Now if I move P outward a little bit, I change the eccentricity. Now a first thing that I just noticed is if P lies on the incircle right here, my conic degenerates to a parabola, which is similar to the case with the antipodal vertices seen on the previous video. Okay, if P is outside of this incircle, so let's keep going. Now I've degenerated to a hyperbola. Well, not degenerated, I've come back to sort of a more usual conic, a hyperbola, right? I can rotate P on the circle and I can see this family of hyperbolae. Let's zoom out a bit and then rotate P. You can see that it's a family of hyperbolae. One of the foci of this hyperbolae is O, and P continues to lie on the major axis of this conic, which was the case when P was interior to the incircle. Okay, I got the same phenomena, so there's nothing new here. I go to the incircle, I got this parabola. Now if I'm on the circumcircle, I get a degenerate case where all my x3s, by definition, are going to coincide with O, so there's no parabola or conic defined here. Now if I'm outside of the circumcircle, I go back to this hyperbola case, okay, and so forth and so on. Now what a new thing that I want to show in this video is that this property extends to any n-gon that is regular. So let's try, for example, a hexagon. So here's a hexagon, still getting a family of hyperbolae. They seem to be rigidly rotating about center O. And center O, I'm just going to eyeball it here, is a focus of this family of hyperbolae. Let's put P on the circumcircle. I get, by definition, the same kind of degeneracy because all the circumcenters of all of the triangles that I'm considering here are going to be, by definition, okay, inscribed in that circumcircle. So all the x3s are going to fall upon O. This is not a fun example. But if I go to the incircle, I repeat the phenomenon that I saw before, which is you get the x3s, the circumcenters of each one of the subtriangles, to lie on this beautiful parabola. Now this is very elementary, right? But I don't know if this has been described before. Let's look at n equals 7. Right now I'm basically slightly inward with respect to the incircle, so I'm getting an ellipse. Okay, and if I rotate my P around this inner circle, let's go ahead and make this a little smaller so you can investigate this a bit better. You can see here that if I rotate P on a circle centered on O, my ellipses seem to be simply rotating rigidly, and the focus is pinned at O, one of their foci, right? Is pinned at O, there's another focus over here. Now, the beautiful result is if we go to the incircle location, I repeat the phenomenon, I'm getting a parabola. So I've done this very experimentally. If we go to n equals 8, and you get the same phenomenon, I'm on the incircle, I'm getting a parabola, okay, for n equals 8, and I can go to n equals 9, go to the incircle of n equals 9, I get a parabola as well, okay? So it looks like what we experience in n equals 5, okay, extends to all regular n-gons, so this suggests that we have an algebraic property here that is slightly deeper, algebraic property of the complex roots of unity, right? This vertex here on my regular polygon is always placed without loss of generality at 0, 1, and my O is at 0, 0. Sorry, this is placed at 1, 0, so x equals 1, y equals 0, and O is at 0, 0. And you now have the vertices of this regular polygon, which are simply the 5 roots of unity. And it looks like this harmony is conspiring with the idea of a circumcenter, right? If I compute circumcenters of various triangles, okay? So here's a triangle, one sample triangle. Here's its circumcenter. It looks like they want to fall always on a conic for any n equals 9 to make it more asymmetric. These 9 circumcenters of these 9 subtriangles, fan of 9 triangles here, okay, with one apex on P and bases on the sides, all the 9 ones want to fall on a conic, and that one focus of this conic is O, and P always lies on the major axis. Now if you go back to the previous video, I did that same kind of construction, but instead of computing circumcenters, I was computing the so-called antipodal points. You can see here that the 9 antipodal points also fall on a different conic. Okay, here's the x3 conic, here's the antipodal conic, but they both have major axes along OP. Okay, and they both have the same behavior, that if P lies on the incircle, I get a parabola. Incidentally, another eyeballing that I can hazard here is that the focus of the parabola in the case of the antipodal is an antipode of P also on the incircle. So it's probably going to be in here. Just by symmetry, I'm going to hazard that the focus of this guy will be the antipode of P with respect to O on the incircle. Okay, so here's the antipodal case, and here's the x3 case. Here, the focus of the parabola or of the conic is outright the center of the system, and this, for the x3 case, is the case for all locations of P, right? I always have a focus that lies on the center. This is not the case for the antipodal. I don't have a focus, nor do I have a center here. The only property here is that all the antipodals, like the x3s, lie on in this case, a 9-point conic. Okay, I'll see you on the next video.